Okay, we're going to look at question 90 now. A flask contains a mixture of compounds A and B. Both compounds decompose by first-order kinetics. These are separate reactions. The half-lives are 50 minutes for A and 18 minutes for B. If the concentrations of A and B are equal initially, how long will it take for the concentration of A to be 4 times that of B? All right, well, two reactions. So A is being converted into something, maybe some products. B, the same thing, being converted into some products. What we're told is that these are both first-order kinetics, first-order reactions. That's nice. We can write a form of the integrated rate law. I'm going to leave the bracket notation out, so I'm just going to put A over A naught is equal to minus K for that reaction. I'll put A as a subscript times T. We can write a similar equation, a similar rate law for B. The natural log of B over B naught, these are concentrations, is equal to minus KB, that's the rate constant for reactant B, times T. Okay. We want time to be the same for both of these. We want to find the point in time where the concentration of A is 4 times that of B. So we are told that the initial concentrations are equal. So let's make them simple. Let's make the initial concentration 1 molar, just to simplify things. The natural log of A over 1 would just be the natural log of A. So that simplifies that. And we'll do the same thing for B. We'll assume the initial concentration is 1 molar. So that will simplify to B over 1. That's just B. Remember, these are concentrations. Now, we don't know what these rate constants are. We don't know the value of Ka or Kb. We need to know those to figure out what the time is. If you look at both of these equations, we're not going to be able to figure out what T is unless we know the values of these Ks. So let's figure out Ks initially. The value of K for a first-order reaction is related to the half-life. The value of K is the natural log of 2, which is approximately 0.693. I'm just going to leave 3 sig figs in there, divided by the half-life. That's for first-order kinetics. The relationship between the rate constant and the half-life is different for second-order kinetics, but for first-order kinetics, that's the relationship. So if we take the natural log of 2, which is unitless, and divide that by the half-life, we get 0.01386. And the units are reciprocal minutes. So there's your rate constant for the reaction A. We will do the same thing for B. Kb would be the natural log of 2 over the half-life. I'm going to leave the units out after this calculation for the rate constant because it takes up a lot of room. So we get 0.0385 reciprocal minutes. So we now have the values of K. The next step in this problem is to say that we know that the concentration of A is going to be 4 times the concentration of B at the time point that we're interested in. So let's figure out how to deal with that. If the concentration of A is 4 times the concentration of B, we could say that the concentration of B is 1/4 the concentration of A. Or concentration of A over 4. That's another way to write it. So let's use that. Let's use that for this second equation up here. We're going to substitute in the concentration of A over 4 for the concentration of B, because at that time that's what should be occurring. So now let's bring them both back down. ln of A equals minus Ka times T, which we know the value of K, and now the natural log of, again, I'm going to get rid of the bracket notation just to make it look a little simpler, is now minus Kb times time. So now we have two equations, and 2 unknowns instead of 2 equations and 3 unknowns. Initially we had A, B, and T were unknowns. Now it's just A and T, two unknowns. So now this is something we can solve algebraically. So what I'm going to do is I'm going to say the following. ln of A is negative Ka times T. So I'm going to substitute here. Let's take the second equation, and I'm going to rewrite it as ln of A minus ln of 4. That's a property of logarithms. The natural log of a ratio is the natural log of the numerator minus the natural log of the denominator, and that's equal to minus kb times t. So now what I'm going to do is I'm going to say that the natural log of A is minus Ka times t. I can put that right in there. So let's try that. We would now have the natural log of A is minus Ka times t minus the natural log of 4 is equal to minus Kb times t. Ooh, look at this one now. Now it's one equation, one unknown. We can solve for that now. So here's how we could go about doing that. Let's figure out what the natural log of 4 is. So 4, the natural log is 1.386. So this would be negative Ka times t minus 1.386 equals minus Kb times t. Now let's combine like terms. This is a constant times time, a constant times time. Let's combine those two terms. So I'm going to add Kb times time, this term right here, to both sides. So now I would have minus Ka times t plus Kb times t equals, not equals, minus 1.386. I've added this to both sides, so now that's equal to 0, right? If I take minus kbt plus kbt, that's equal to 0. Now we can move this to the other side by adding it to both sides. So now we have minus Ka times t plus Kb times t is now equal to 1.386. Okay? I've added this to both sides. Now let's combine the like terms. Let's just factor out t. If we factor out t, we get negative Ka plus Kb. And that would now be equal to 1.386. This is really nice. It's working out better. So now we can just divide both sides by what's in the parentheses, negative Ka plus Kb. So time would be 1.386 divided by negative Ka plus Kb. Now I won't go ahead and do it, but if you actually think about it a little bit, this is the same as Kb minus Ka. Right? So let's take the 1.386 and divide that by the negative Ka. Did we find Ka? We did. It's way up here. Let's come back to it. Ka is 0.01386, and we found Kb also. So dividing that by 0.01386, which is a negative number, plus 0.0385. And what do you get? You get 56 minutes. So this comes out to, substituting all of these values in, you get 56 minutes. I'm not going to worry about 3 or 4 sig figs on this one. It's roughly 56 minutes. And so does that answer make sense? Let's think about it a moment. After 50 minutes, the concentration of A should be, so let's write it this way, concentration of A, and let's write time in minutes. It starts off at 1. After 50 minutes, it should be down to 0.5. Okay, well, this is around 50 minutes, not exactly 50 minutes, but it's close to it. So now let's consider B. Well, B starts off as 1 molar also, but after 18 minutes, it's a half. After another 18 minutes, it's half of that. So it'd be after 36 minutes, it would be 0.25. Another 18 minutes would be 54 minutes. It would be down to roughly a quarter, 0.125. And so somewhere around 50 minutes, it would be 0.125. 56 minutes, actually. I'm sorry, 54 minutes. So somewhere around 50, the ratio is 4. It's not exactly 50 minutes, it's 56 minutes. The reason that it doesn't work out here is because the decays are nonlinear. They're exponential decays. So we really have to use the logarithmic functions here, the integrated rate laws, to get the actual time. But it's somewhere around 50 minutes, which for us, we got 56 minutes. So this is a way to connect two different reactions with different rate constants. Essentially what happened was A decays more slowly because it's a smaller value of a rate constant. B decays more rapidly because it has a larger value of a rate constant. We can use those equations in order to figure out at what point the concentration of B will be 1/4 that of A.